Francesco, when you start and I start recording. Yeah.
Okay, yeah. Should I go or should you say something in the beginning?
Oh no, there you come. There you come. Actually, yeah, I just did
Okay.
record it. Yeah.
Okay, so we can start. Okay. Yeah. So welcome back, everyone, to this nice workshop. The first speaker of this session is Volodymyr Takisto, who will tell us about the primordial origin of stellar mass black holes. So whenever you are ready, Volodymyr, you can go ahead.
Okay. Thank you very much, and I would like to again thank the organizers for the very wonderful workshop and for putting this together. So I will tell you about how we can say something interesting about the origin of stellar mass black holes and try to relate this to their possible primordial origin. So let me start by just reminding you and kind of stressing the fact that black holes definitively exist, and this is now an undeniable fact, and they're central in astronomy. Of course, one of the key pieces of evidence is, the supermassive black hole in our galactic center, the Sagittarius A star, which has been discovery of which has been commemorated by the Nobel Prize in 2020, and the movie that you just saw. This is the rotation of the various objects around the galactic center from the UCLA Galactic Center group, which hints at a massive big supermassive object in the middle, which is a supermassive black hole. Of course, earlier this year, in 2022, we also had the first image of the black hole in the center of the Milky Way, which further brought this picture together. And obviously, we are now living in the age of gravitational wave astronomy, as of course hinted by the discovery of the mergers in gravitational waves and binary black holes. So all of this brings a coherent picture together that, as I said, the black holes definitively exist and they play a very important role in astronomy. While conventional black holes, that is astrophysical black holes, it can be roughly associated with the picture of formation of going through some star phases, and then later on, if the star goes supernovae, it can form either a neutron star or a black hole. Actually, you can have black holes formed even before or unassociated with star formation in the early universe if you just take a scoop of an overdensity and that collapses. And those are primordial black holes. This has been already postulated over 50 years ago, so this is a very rich field by the pioneering work of Hawking, Zeldovich, Novikov, Carr, and of course many others. But one very important point that I would like to stress is that, in a sense, primordial black holes could be a dark matter candidate, but a standard model type of dark matter candidate. Of course, it benefits significantly to have beyond standard model physics, and there's a plethora of formation mechanisms for primordial black holes, which I unfortunately do not have time to go into in this talk. But in a sense, primordial black holes are a standard model dark matter candidate. And of course, it's great to look at dark matter that exists. Let me just briefly remind you of the status of primordial black hole dark matter, and I would like to, of course, point you to great reviews, for example, by Misao Sasaki, Bernard Carr, and others. Here on the y-axis is the fraction of primordial black holes in dark matter. On the x-axis is their mass. You have constraints on the left associated with Hawking operation, then a variety of bounds associated with microlensing. Then going farther to the right, there are gravitational waves. These are the LIGO events. And there's a variety of other constraints, which can be broadly characterized as associated with accretion emission, but there's also some other things which I don't have time to go into. But this is the general picture of one of the most interesting regions of the parameter space for primordial black hole dark matter. Especially intriguing is that within the last several years, it has been appreciated that as people have been revisiting some of the older constraints, there is now a parameter space spanning several orders of magnitude and mass, where primordial black holes would constitute the entirety of the dark matter abundance, which of course is very exciting, and people are actively trying to figure out how can one test this. Well, one interesting possibility is that to look at very interesting new hints how such tiny primordial black holes that make up dark matter that reside in that region could manifest that. And one particular hint is how they could be associated with making gold astrophysically. Let me just remind you that the origin of heavy elements such as gold is a major long-standing problem in astrophysics, already spanning decades, and there has been a lot of work on this. And of course, neutron star mergers, when they collide, they emit neutron-rich material, which undergoes our process nucleosynthesis and produces heavy elements. And with the 2017 neutron star merger multi-messenger detection, this has been hailed as a big breakthrough in this problem. Of course, neutron star mergers are great, but recent work show that perhaps they are not enough. And so the problem of the origin of heavy elements seems to still be open and persists, and has been picked up by some science media. Something is raining gold across the universe. We do not know what it is, and this is a major issue. So as I promised to you, let me now tell you how tiny primordial black holes can make gold. Well, if tiny primordial black holes can be efficiently captured by neutron stars, for example, in the dark matter and neutron star-rich environments, such as galactic center, then they could be swallowed, and as they eat and explode the neutron star from the inside, this could again result in emission of neutron-rich material, and similar to neutron star mergers, result in formation of heavy elements through our process nucleosynthesis. And this is, of course, a very exciting possibility. But what is even more exciting is that this is just one example of possible hints of such small primordial black holes making dark matter. In fact, neutron stars and white dwarfs, more generally, are excellent primordial black hole laboratories. Aside the heavy elements that I just mentioned to you, they can make positrons, which could be associated, for example, with the well-known 511 keV galactic center access, which, by the way, could be fully explained just with regular neutron star mergers. But they could also result in completely novel type of signatures, for example, orphan kilonovae, but without associated gravitational wave emission. So, for example, in the case of a neutron star merger, you, of course, also have a kilonovae afterglow, but you also have a merger coincidence, which is the multi-messenger signature. But here you do not have this. You can also have a source of fast trigger bursts, which are now very hot in astrophysics and constitute very exciting signals to do a lot of interesting astronomy. If there's some accretion disk forms, then perhaps they could form, they could lead to gamma ray bursts. But what is more exciting and relevant for the topic of this workshop is that they would also lead to a population of a so-called transmuted solar mass black holes, as I coined them in that study shown right here, where the small primordial black hole that eats a neutron star when it captured will result in a formation of a solar mass black hole that will remain. And this leads me to ask a more general question about the origin of such black holes. But before I go to this point, let me just briefly touch upon a little bit more on transmuted solar mass black hole mergers and how can these be a novel source of events to look for. In particular, if you have, for example, a neutron star binary, and one neutron star got poisoned by a small, tiny primordial black hole contributing to dark matter that later eats the neutron star, you will have a solar mass black hole with a neutron star binary, which could result in interesting gravitational wave events for LIGO type of instrument to search for. Of course, you can have other type of binaries, for example, white dwarf with a neutron star. White dwarf has different properties than neutron star, and so once it is transmuted, this will lead to a different population of black hole neutron star events. And you can also have, for example, interacting white dwarfs and so on. But all of these are just different possibilities, which highlight how transmutation of a compact object by a tiny primordial black hole could lead to very interesting solar or subsolar mass black holes, which are particularly intriguing for gravitational wave observations. But let me go back to the question which I asked earlier about the origin of solar mass black holes. So why is this an interesting question? Well, actually, in astrophysics, in textbook astrophysics, you do not expect solar mass black holes. And here, by solar mass, I mean broadly black holes below, let's say, 2.5 solar masses. And this is associated with a neutron star stability limit, so-called Tolman-Oppenheimer-Volkoff limit, where you would expect neutron stars to reside in not black holes. So to a wide range of people in this community, detection of such solar mass black holes would be a hint of some really new exciting physics beyond textbook astrophysics, such as either primordial black holes or, as I mentioned, transmuted black holes, which could be from tiny PBHs eating neutron stars or white dwarfs, but also people have been extensively studying this within the context of particle dark matter accumulating and collapsing inside, and also resulting in solar mass black holes when they interact with neutron stars or white dwarfs. So all of this is great, but why is this relevant right now? Well, LIGO is already detecting candidate events for such solar mass black holes. And so then the question becomes, if these are, of course, really solar mass black holes and not a misidentified neutron star, how do we tell their origin? Well, in fact, one simple, elegant approach to this problem is to just look at the mass distribution of these objects. In particular, transmuted solar mass black holes, which originated either from small PBHs or particle dark matter interacting with neutron stars or white dwarfs, should follow, for example, the neutron star mass distribution, which we know from supernovae astrophysics. And by plotting candidate events on the expected distribution of neutron star masses, you can already make very powerful statements even without doing any complicated statistics. In particular, you can say that, for example, large solar mass black holes, let's say bigger than 1.5 solar masses, such candidate events are unlikely to be from dark matter neutron star interactions. And so just doing these simple comparisons, you can already make profound statements about the origin of black holes and dark matter. Well, let us move on to slightly bigger masses and talk about the mergers themselves, which are of particular interest for LIGO observations. In particular, black hole neutron star mergers. So one of the reasons that primordial black holes got so much excitement in the recent time is, of course, that primordial black hole binary mergers have been directly linked with the black hole gravitational wave events as discovered by LIGO. In a lot of pioneering works, for example, by the group of Mark Minkowski, Misawa Sasaki, and others, as well as I know that there are experts in the audience who also have contributed to these efforts. But what about black hole neutron star mergers? So this is actually another very important class of events, and they are particularly relevant for multi-messenger astronomy, because black hole neutron star mergers can also have ENM associated emission, just like an SNS for some parameter space. So this is very exciting, and recently came to light because LIGO already started detecting candidate events and observing this. So then the natural question is, if there are such events, and of course, with LIGO upgrades and so on, we'll expect a lot more in the future, can they be with primordial black hole origin? Can primordial black holes contribute to these events? Well, there is one key difference of PBH neutron star mergers versus PBH mergers. And that is primordial black hole neutron star mergers can only happen after star formation, while PBH mergers can happen even before star formation. And then you can find what is the rate of such interactions. For example, you can look at the distribution of dark matter versus the distribution of the neutron stars, convolute these two distributions, and then take the scattering cross-section, for example, associated with two-body scattering and gravitational wave emission, which should be the dominant and the simplest channel. And then you can also look at different halos where this could occur, and plot what is the merger rate per halo, and then also integrate this over the population of the halos that you have. So here on the left is the plot which shows the merger rate per halo. This is in units 1 per year. On the bottom is the mass of the halo. So for the case of a Milky Way, this would be around 10 to 12 M-sun. And here, the red lines correspond to PBH. The lines on the bottom correspond to PBH neutron star mergers. And the reason they look different is that PBH neutron star mergers also need to take into account the stellar distribution. This is not just dark matter mergers. This is dark matter interacting with things associated with star formation. After this, you can integrate over your population of halos. And then you will notice that on the plot on the right, the primordial black hole neutron star total rates are significantly subdominant compared to what is relevant for observations, for example, in units of order 1 per year per gigaparsec cube. So what does this mean? This means actually very profound consequences. Namely, that the observed neutron star black hole events are actually astrophysical in origin. And future events would also be astrophysical. But more intriguingly, this statement is true even if PBH significantly contribute as mergers to black hole gravitational wave events in LIGO. And the reason for this is, as I mentioned earlier, PBH mergers can contribute from before star formation. So even if PBH neutron star mergers are suppressed and are subdominant, PBH can have enhanced rate even before star formation and contribute additionally compared to these events. So this is, of course, a very interesting possibility, and this shows that, of course, PBH mergers is something very important to further consider in the context of LIGO signatures. This also carries further implications, is that such events would not significantly contribute to multi-messenger emission, which is just a corollary of the statement that these event rates are subdominant. Okay. Well, let me now mention that there's a very interesting novel test how one can say something interesting about the role of PBH dark matter for LIGO type of signatures. So stellar mass black holes, of course, relevant for LIGO, can only comprise a subdominant fraction of dark matter abundance, as has been known from a variety of constraints. However, what this means is that during the structure formation, these PBHs will seed massive halo dresses around them of the primary dark matter component, for example, composed of axions. This could lead to a variety of intriguing signatures in very specific models, for example, enhanced annihilation rates in the case of WIMPs, or some radio emission in the case of axions where you have PBH dressed in axion cloud interacting with neutron stars, for example. But is there a general way to detect these dressed primordial black holes directly? Well, in fact, there is, as we identified in this work, and this is associated with strong cosmological lensing, for example, in the case of fast radio bursts. This is just a schematic of how this would work, that if you have a black hole dressed in a dark halo, then strong lensing will be sensitive to this halo. In fact, one can show that local lensing is insufficient, but if you have, for example, lensing by fast radio bursts, which are generally distributed around redshift 1 and cosmological distances, this becomes a prominent signal. In fact, one already starts probing interesting parameter space with the CHIME FRB catalog, which is now growing, and this is a very active area of astrophysical work. And with around 10 to the 5 fast radio bursts, one would actually be able to start to probe such dressed primordial black holes in the region relevant for LIGO. So here, the shaded regions on top, this is without the halos, just naked, bare primordial black holes. And here on the bottom would be how would the probe look if you have this dressed halo primordial black holes. So what I presented to you is a novel way how one can directly test these dressed primordial black holes and identify the consistency of such scenarios, and also test in future events relevant for gravitational waves. In fact, the scenario I presented to you is even more general than FRBs and could be applied to other lensing sources, such as supernovae or caustic crossings, which is something that will be done in future work.
Sorry, Volodymyr,
yeah.
9 minutes left.
Yeah, I will finish before then. Yeah, thanks. Let me now move on to slightly higher masses, also of relevance for gravitational wave events, and those are the intermediate mass black holes. So we discussed from smaller masses to solar mass black holes to larger mass black holes relevant for gravitational events. What about intermediate mass black holes? And again, this became very relevant recently. Of course, there have been hints before and some claimed detections, but LIGO recently identified first definitive observation of such intermediate mass black hole event. So then again, the question is, could those be primordial? Of course, as we know from the constraints plot that I was showing earlier, there's a variety of constraints already in that region. However, let me tell you about a new general cosmology independent observable that is very simple, but can test a very broad parameter space of primordial black holes. And that is interaction and heating of gas within some particular system. And the idea is very simple, is that if you have a system of gas and you have black holes flying around, they will interact with the system and deposit energy through a variety of mechanisms. For example, through dynamical friction or gravitational drag, with formation of accretion disk, there will be emission of photons, and there could also be outflows or baryonic winds. But all of these are just different mechanisms of depositing energy. So once black holes in a system of gas are dumping energy through a variety of mechanisms, by looking at some particular systems and knowing their properties, you can ask what is the cooling versus the heating rate of the system. And in fact, it turns out that this is a very powerful probe of primordial black holes and does not rely on any cosmological assumptions. In fact, if you have spinning primordial black holes, they become exceptionally favorable for formation of yet another strong contribution, so-called jets, which people now very strongly believe is associated, for example, through Blanford's Knight mechanism. As recently from image of M87, we learned there is a strong magnetic field as required for such formation. So this would be one of the dominant possibilities. But with spinning primordial black holes, if you form jets, then in fact, this would be another deposition, strong deposition of energy, even more efficient than one I've described previously. For example, the jet can hit interstellar medium. There will be some shocked cocoon of material. Basically, it's a heat bubble that will expand. But this is just another contribution to what I described as a mechanism of dumping energy in the gas system. And it turns out that if you compare cooling versus heating of a favorable system, in particular Leo T dwarf galaxy, which has some nice properties, you can probe primordial black holes over many orders of magnitude in mass range, including the range relevant for light. And you can do the same type of exercise, actually, if you're doing Hawking operation for tiny primordial black holes. You can also ask how much they can, for example, heat a system of gas. So let me now summarize. So as I mentioned, primordial black holes are, in a sense, a standard model dark matter candidate, which is, of course, very exciting. We know they exist and they contribute to importantly to astrophysics, the regular black holes, but with some help of beyond standard model physics, we can make them in the early universe efficiently through a variety of mechanisms. This is really a renaissance in the field, especially due to synergy with multi-messenger astronomy breakthroughs. And as I mentioned some examples, there are strong connections of primordial black holes in terms of astrophysics to long-standing astronomical puzzles and a variety of very exciting signatures to look forward to. So perhaps they're already lurking in the data, perhaps the LIGO data or some others. So it is essential to confront new observations as we go forward. And hopefully with all of this, we are marching closer to understanding what is the role of primordial black holes in dark matter and in physics. Thank you very much.
Thank you, Volodymyr. Very interesting talk. Okay, we have time for a few questions. I don't see questions so far. Nobody has raised hand. So maybe I can ask a very simple and stupid question. Do you have in mind what you will be able to add to this story with the future detectors like LISA and others?
Yeah, great question. So LISA is, of course, as elaborated by experts in other sessions of this very nice workshop, is probing different range of gravitational waves. So there's another story associated with that. But if you're asking what can you do more generally with future observations, you can do a lot of it very interesting, for example, statistical analysis. So while I have not covered this, there is right now a very active work by a group of Antonio Riotto and other people, for example, trying to understand how much primordial black holes statistically can contribute to the existing LIGO data. So with more observations, these statements will be made more sharp and precise. So that would be one example.
Any other question? I don't see any. I'm sure we can continue the discussion during the discussion afterwards. So let's thank again Volodymyr. And
thank you very much.
Thank you. We go to the next speaker, who is Raffaele.
Yes, I'm here. Can you hear me? Sorry. I'm
Yes, yes.
moving around. One second. So let me try to share screen. Okay. All right, so I'm ready whenever.
Yeah, please. So Raffaele comes from Saclay, and he will tell us about resonant cavities for gravitational wave detection. So please go ahead. You have 30 minutes.
Yeah, so thank you very much for the invitation. Well, please stop me if I go over or if you heard this already, because, well, I've been talking about related topics at a few related workshops. So please feel free to interrupt me and ask questions or ask me to go faster or slower. Indeed, so as the title says, I'm gonna tell you about some ongoing efforts of trying to detect gravitational waves using microwave cavities. I should say that I'm a theorist, so I will do my best to give you the details of the experimental apparatuses, but well, I'm certainly not the person building it. So if some of you are gravitational wave experimentalists, you might find some of my answers a bit lacking, but okay. With this disclaimer in mind, let me move on. So, well, as you know, there is a vast spectrum of gravitational wave frequencies out there, and ideally we would like to explore all of it. Most detectors are at what I will colloquially call low frequencies. The reason is that there is a bound on the largest gravitational frequencies that we expect from astrophysics, around 10 kilohertz, and I'm sure you're all familiar with it. But what I'm going to talk about today is detection strategies that go farther at higher frequencies. So they try to go beyond this bound. And the reason is mainly that going to this high frequency essentially means having a guaranteed non-standard signal if you find anything. The reason why a particle physicist like me is interested in this kind of gravitational waves is essentially causality. So if you ask what's the largest wavelength that you can have at a given time in the history of the universe, that's bounded by the horizon, so by Hubble. And if you translate this into particle physics scale, you see that going to 100 megahertz in frequency might be potentially very rewarding, because it would mean probing very high temperatures, so phase transitions or dynamics occurring at energies that we might never be able to probe with colliders. And I'm sure that, well, you're all familiar with this, but I wanted to put the talk a bit into context. The problem with this kind of gravitational waves coming from primordial phenomena is that typically they have a stochastic spectrum, so they're not coherent over very long time scales. The typical coherence is comparable to the inverse of the frequency. And so this makes them extremely challenging to detect experimentally. In practice, what I'm going to show you today is going to be sensitive mostly to coherent sources of gravitational waves. And at these high frequencies, this could be still extremely interesting. So still coming from signals that will signal that there is something beyond our current description of nature, but a bit more model dependent. So it's not as nice as just saying, okay, from causality, I'm expecting to probe early times. Here, you have to assume that your theory contains either a primordial black hole with a special mass, or a primordial black hole and some light particle that can produce gravitational waves from superradiance, and so on. So this will be the main potential sources of signal at these high frequencies that I'm going to target. So I think I've bored you enough with an introduction, and what I'm going to focus on in the first half of the talk is going to be this kind of interactions between graviton and photons. In reality, we're always going to be in a regime where we're going to look at this classically. This is just a picture for particle physicists, but well, so this is the main character of the first half of the talk. So trying to detect these high frequency gravitational waves using electromagnetic field. And well, there is a simple reason behind this, which is the fact that at these high frequencies, electromagnetic fields are the objects that we are able to manipulate best in the laboratory. So if you ask what's the classical field for which I can build up the largest amplitude and its frequency the best under control, that's an electromagnetic field. So this is why conceptually you would like to start here to try to detect gravitational waves at these frequencies. And I'm going to start with an analogy with axion detection, because we will see that contrary to the common law, it's possible to recast some results in axion dark matter searches into bounds on gravitational waves. And so the reason why axions are useful at all when you start thinking about gravitational waves is that if they are dark matter and they are light, they look a lot like a gravitational wave in the sense that they are a classical field, which potentially is coherent for a long time. So I've written up here at the top of the slide a simple cosine. If we assume that this particle is dark matter, we know the amplitude, so it's proportional to how much dark matter there is around us. And the frequency of this cosine depends on the mass. And what's nice about this classical field, as I was saying, is that it's very coherent. So this very simple picture here of having a single cosine, it's not true in general, but it's true for at least 10 to the 6 oscillation periods. And it's also true over a distance that is about 1,000 times longer than the inverse mass. So it's a very good description from the point of view of an experiment that wants to look for that, because typically, if you know the frequency, you want to try to match a resonator to it. And then these coherence properties make it such that your typical resonator will actually see these monochromatic sorts. In addition to this classical field behavior, the axion also has a coupling to two photons, just the one that we want to target from gravitational waves. And just like gravitational waves, the most appealing theoretical models out there predict a tiny signal. So if you turn on a background electric field and imagine that this axion particle makes up dark matter, so it's all around us and it's crossing our experiment, then the photons that come out of these interactions are roughly 10 to the minus 21 of whatever you put in. So at face value, it seems just as difficult as looking for a gravitational wave. In reality, it's a bit easier because you know exactly the waveform, and so it's much easier to design a search for this kind of object, because if indeed it's dark matter, it's really that simple cosine. So you can literally match a resonator and be done with it. And in fact, this is one of the most successful concepts for axion detection. So you make a box which you can make out of conductors or superconductors in such a way that you're breaking translational invariance for the photon, meaning that effectively the photon is getting a mass proportional to 1 over the size of your cavity. And said in a less fancy theory way, you have some normal modes for your electromagnetic fields inside this cavity, which have characteristic frequencies proportional to 1 over the size of the cavity. So essentially, you built an electromagnetic resonator. And you can then match the size of this resonator to the mass of your dark matter particle and wait. And if your resonator has a large quality factor, so it behaves like an harmonic oscillator for many oscillation cycles, you can build up your signal and go from that completely unobservable 10 to the minus 21 number that I showed you before to something maybe in the ballpark of 10 to the minus 10 or so that you might be able to detect. And this very simple concept has been quite successful in the realm of axion detection. And what I'm going to show you in the next few slides is that you can literally take axion experiments that already exist. Here, there's a list of a few of them on the left of the slide, and recast their sensitivity onto gravitational waves. And you can see that, well, this is the final result already. You can see that, again, if you just look at the numbers, you're seeing strains that look pretty promising and nice, something around 10 to the minus 22, 21, so what you expect from a gravitational wave. Of course, if you look at the small print in this slide, so start looking at the frequencies here, so we're looking at gigahertz gravitational waves, then you'll see that this number is not that good. So there is no primordial source that can give you a strain of this size. So if you just assume that this primordial source has to respect the BBM bound, automatically you're about 10 orders of magnitude smaller in strain. But okay, this could still be interesting for the class of more model-dependent signals that I mentioned at the beginning of the talk. And I'm going to spend a few slides building up to this result because, well, there was something that was not completely understood in the literature, and even if it's simple, I think it's worth to put it out there. So how did we get to recast these bounds on axions onto gravitational waves? So in both cases, you can write the interaction with the electromagnetic field in terms of an effective current at the top of the slide. And in both cases, well, these are not really covariant vectors in the GR sense. So they don't transform in a simple way. And in both cases, they depend on the background field that you turn on in the laboratory. So this effective current, let's say, formalism, it's useful if you really have in mind the kind of experiments that I described before, where you turn on a large electromagnetic field in your laboratory and you look for something coming out. Then there is a natural separation between what part of the electromagnetic field goes in the current and what part goes into your signal. In other cases, this language of the effective current might not be very useful, but for us in this talk it is, so we're going to move forward with it. So up until that slide, you might say, okay, I have an effective current for the axion, one for the wave. I just compute both, match them, and I'm done. I can find the sensitivity of this experiment to gravitational waves. It's not quite so simple because of the large gauge redundancy of GR. Typically, well, there are at least two reference frames that make sense to consider. There is the so-called proper detector frame, which is a system of Fermi normal coordinates with the center of mass, with the origin corresponding to the center of mass of your detector. And then there is the TT frame, where typically the vast majority of gravitational wave calculations are done when it comes to producing them. And let me tell you, how does your laboratory look like in the two frames? So in the proper detector frame, as the name suggests, your laboratory looks exactly how you expect it to look. So it looks like it would look in Newtonian gravity. So if you have some uniform magnetic field that you turned on, it remains uniform. If you have an infinitely stiff wire that you're using to measure electromagnetic fields, it remains fixed at its place. And then if a gravitational wave arrives in your laboratory, it's going to generate a small oscillating component of the electromagnetic field, starting from your large background field that you can pick up with your probe. So the description of your laboratory is very easy in this frame. On the other hand, the metric looks nasty. So if you call HTT the metric in TT gauge, in this frame, well, okay, you don't have a simple metric anymore. So you might want to change coordinates and go to the other frame where you actually computed your gravitational wave signal. And if you do that, well, of course, the metric looks much nicer. Now I'm just showing you a gravitational wave going in a certain fixed direction along the z-axis, but it's the same as this. So also in the proper detector frame, I was showing you a gravitational wave going in a fixed direction that was the z-axis. So you see that there is a huge simplification, and that's to be expected. However, to get this huge simplification, we performed a coordinate transformation, which is not constant in time. And so you have to transform also your laboratory. And when you do that, you get a complete mess. So what's infinitely stiff in your intuition and in the proper detector frame starts to move a lot in this TT frame. And if you start with a uniform magnetic field, you end up having an oscillating magnetic field. So it's really complicated to describe your apparatus. And in fact, I mean, I know that up to now it's all obvious, but this led to some mistakes in the literature. So for example, if you turn on a static magnetic field in your laboratory and imagine that you have a wave parallel to it coming in, then, well, the effective current in the TT frame is 0. And this has led people to some wrong conclusions. So to say that there is no signal in this frame, in this configuration, this is false for two reasons. So the first one is that it's impossible to prepare a uniform magnetic field in the TT frame in your laboratory, because it would mean that you know exactly what wave is coming in, with what phase, what frequency, and then you are actually preparing a magnetic field that is oscillating exactly at the right frequency, exactly in phase with your wave. That's the only way in which the field would look uniform in the TT frame. And secondly, even if you were some sort of god of experimental physics and you could do it, you would still see a signal, because even if the effective current is 0, your whole apparatus is moving in this frame, and so you still pick up a current in the wire that you would not pick up in flat space. And so, okay, this I told you all this story in the simplest possible terms in a toy model, but then in practice it's relevant to us, because if you do the wrong calculation for these action experiments, you get that the signal is 0. But instead, it's non-zero at all for the reasons that I just said. And if you do the calculation properly, which in our case means choose the proper detector frame where everything is simple except for the gravitational wave, then you get the result that I showed you before. So if you want a few more details, what we've been doing is to compute this effective current in the proper detector frame, and then expand the electromagnetic fields in the cavity into normal modes, and effectively just do a simple classical calculation where you solve Maxwell's equations in this basis of normal modes and with this effective current as a source to see what your signal is. And the only extra complication that you need to take into account is that you're looking for a gravitational wave that's resonating with the electromagnetic modes of the cavity. So it has roughly the same frequency, and as a consequence, since both objects move at the speed of light, it also has a wavelength comparable to the size of the cavity. And so it's not enough anymore to use the metric in the proper detector frame at leading order, as it's usually done, but you have to resum everything. It turns out that it's possible to resum everything, and you get the ugly result that I was showing you before. One simple way to see why it's important to resum everything is trying to do the calculation without resumming everything. If you do that, you're going to find that the leading term, so this 1 here corresponds to the first term in the expansion of the metric, so the one with a Riemann tensor and 2 coordinates, integrates to 0 over the volume of the experiment. So again, if you didn't resum the metric, you would end up concluding that there is no signal. But in reality, okay, already the next term is not 0 anymore, because this sign has a counterpart, and so you get a sine squared integrating over 2 pi, and it's not 0 anymore. All right, so all this leads you to the result I was showing you before. So I think this is an interesting result because these experiments already exist, so they essentially need to do 0 effort to set these bounds. On the other hand, as I was telling you before, this is not really pushing into physically motivated parameter space for gravitational waves too much. One last, let's say, well, not really, but maybe curiosity about this setup is that the coupling of the gravitational wave with the electromagnetic modes of the cavity depends in a non-trivial way on the angle between the gravitational wave and the axis of the cavity. So typically these cavities are cylinders, so they have some cylindrical symmetry, but you still have one angle in your problem. And you see these angular plots here, which are telling you essentially the strength of the coupling between the gravitational wave and your electromagnetic modes. As a function of the angle at which the wave is arriving on your apparatus. And so in principle, well, if you ever detected one of these gravitational wave, you might be able to point in the direction of the sky where it's coming from, even potentially using a single cavity. But if you have two, even better. Okay, so this was a bit to set the stage for a more interesting, in my opinion, way to look for gravitational waves using the same experimental apparatuses. So let me just check quickly how I'm doing on time. Okay, so I think I'm doing all right.
10 minutes left.
Thanks. So far I showed you what you can do with existing experiments, but there is actually a better way to look for gravitational waves using these cavities. And at the end of this part of the talk, I will also show you comparisons with other ways of looking for gravitational waves in the same frequency range. And this better way is the following. So imagine that now you build a special cavity which is tuned in such a way that two electromagnetic modes are close in frequency. And I'm going to put electromagnetic energy in this mode at omega 0, which is lower in frequency. And then a gravitational wave coming in can move energy from the lower mode to some higher mode, okay? And if I design the geometry of the cavity appropriately, I can do it in such a way that I try to maximize the coupling of the gravitational wave to these two modes. Why this is interesting? Well, it's interesting for two reasons. So I still have this signal that I just described, where the gravitational wave interacts with two photons, and that's already allowing you to, using the same cavity, go to much lower frequencies, because now what's relevant for a resonance is the splitting between the two frequencies. So you can start with a cavity of a certain size, and without changing the size of the cavity or all your electronics, you can in principle scan over a big frequency range of the gravitational wave by just deforming the boundaries of the cavity a little bit. For instance, here you have a cartoon of some sort of fins on the bottom of the cavity that you can move in and out. It's not obvious that this is the best way to do it, but if you want to just change the frequency splitting between two modes, you just need to deform the cavity walls a little bit. So you don't need to build an entirely new cavity of an entirely different size to probe different frequencies. The second reason why this is interesting is that there is a second signal that turns out to be much bigger if you go to frequencies that are parametrically smaller than the typical size, invert size of the cavity, compared to this direct coupling to electromagnetism that we just described. And the second signal comes from the fact that gravitational wave is deforming the cavity boundaries. And this effect can mix electromagnetic modes inside the cavity. And in principle, you can do this resonantly with the mechanical modes of the cavity. So you are matching the gravitational wave to the mechanical resonances of the cavity, and then it's these mechanical modes of the cavity that are mediating the transition between the two electromagnetic modes, like in this picture here. Again, this is a cartoon, but gives you an idea of what's going on. So the gravitational wave is coming in, it's converting into a phonon, so it's in an oscillation of the cavity walls. And then this oscillation of the cavity walls is bumping up energy from one mode at omega n to one mode at higher frequency. Why? Well, why is this signal? Well, I'm going to call this signal mechanical and the other one electromagnetic. So in general, you cannot distinguish them because the gravitational wave is doing everything at the same time. But these two signals are kind of mixed only at order h squared. At order h, you can distinguish them because at order h, the gravitational wave is putting only order h energy into your new mode through the electromagnetic vertex. And so this is totally irrelevant for your mechanical transition. Okay, the mechanical transition is only seeing the order 1 energy in the mode that was already replenished before the wave arrived. And vice versa, you can use a similar argument to show that the formation of the cavity wall at order h is not affecting the electromagnetic signal of the same order. Okay, after this subtlety, let me just get to the meat. So why is this mechanical signal interesting? The reason is the following. So In this case, effectively, you're just computing how the gravitational wave is affecting the displacement of the cavity walls. So you're just solving a simple equation of motion from Newton's second law. You have some force divided by the mass of the cavity. The force is proportional to the Riemann tensor in a simple way that one can compute with standard methods. And on the left-hand side, you have this harmonic oscillator looking object, because again, I've expanded my left-hand side in terms of normal modes of cavity wall vibrations. And so in the end, well, if you solve the equation, you get something that looks like the expression at the bottom of the slide. So there is an enhancement coming from the quality factor of the mechanical mode. This is a factor of 1,000, so it's useful, but not huge parametric gain. What's interesting is that the way in which this signal decouples is like gravitational wave frequency squared over mechanical resonance squared. And this is much better than what we could do before, because mechanical perturbations propagate much more slowly than light. So if you ask, I have a cavity of length 1 over L, what's the typical mechanical frequency? This is much smaller than 1 over L. Indeed, if you take a niobium cavity of roughly the size we're envisioning, your lowest mechanical resonance is kilohertz, which means that before, essentially, you were sensitive only to gravitational waves of order 1 over size of the cavity, so gigahertz gravitational waves. Now you have a forest of resonances all the way down to kilohertz. And up to that frequency, the signal is not decoupling like 1 over omega squared. While before, when you were looking only at the electromagnetic signal, everything was decoupling very quickly as you were going to lower frequency. And I should say that this idea of looking at the mechanical signal is very old. So it dates to the late 70s. And all we're doing in our next paper is showing that the sensitivity from this source of signal is actually much better than people could estimate decades ago, partially because of technology, but partially we also checked well, a few things that I'm going to tell you in the last slides that make it even more interesting than it was 40 years ago. So finally, well, I've already said in words the content of this slide, which is the last one before the sensitivity, so the only slide that you actually care about. So as I was saying before, if you match your gravity wave to the mechanical signal, you can get, say, an electric field in your signal mode that looks like this. So 2 quality factors, mechanical and electromagnetic, and then a dimensionless strain time whatever electromagnetic field you put in. And when you go below resonance, this thing decouples like omega g squared, and this is a bit universal for all these resonances, be them mechanical or electromagnetic. And so the fact that the mechanical frequency, the typical, so the smallest mechanical frequency is so much smaller than the smallest electromagnetic frequency makes you gain a lot at lower frequencies. Of course, okay, this nice signal does not come for free, because you put in your cavity source of noise that is oscillating at a frequency close to your signal frequency. There are all sorts of effects that I have absolutely no time to talk about unless you ask me. These are the leading ones. There are also more, let's say, quantum sources of noise. So, for example, two-level system noise or intrinsic nonlinearities of the superconductor if you have a superconducting cavity. Unless, again, as I said, unless you ask, I'm not going to say anything about all these noise sources, except that we did our homework. So we estimated all of them in as much detail as possible, and we tried to use conservative numbers for them. More precisely, what we really used was what was measured almost 20 years ago by the MAGO collaboration. So this idea in the 80s led to actually build a prototype. And this prototype was very useful for us in terms of benchmark parameters. That's essentially what we used. We went beyond this prototype just in 2 ways, which I'm gonna tell you while at the same time showing you the sensitivity of these kind of ideas. So this is a preliminary estimate of how well these cavities could do for coherent waves. So you see on the y-axis you have a strain. So I'm assuming that the wave is coherent over time scales much longer than that of the experiment. In practice, at high frequencies, it doesn't need to be that long. I mean, it could be 1 second, that's enough. But I can be more precise if you're interested. And you can see, well, a comparison with existing proposals, and you see that these ideas in principle could do better in some frequency ranges. What I find possibly the most interesting about this plot, which is the first thing I want to tell you before I go into the details of the curves, is this dashed line here. So this dashed line, which is called non-scanning. This line essentially is telling you what you could do if you literally took this MAGO prototype, which now is in a museum in Genova, and you isolated it from external vibrations. And interestingly, you don't even need to tune the electromagnetic modes to be on resonance with the gravitational wave. So this MAGO prototype can scan the splitting between electromagnetic modes only in a small range, around a kilohertz. This is due to the fact that the scanning comes from this small cylinder in the middle. So if you change the aperture between the two spheres, you're changing the splitting between the modes. This cannot be done indefinitely, and so effectively you can only be resonant somewhere here. I don't know if you can see my cursor, but well, only around a kilohertz. But that doesn't matter, because we find that what really dominates the sensitivity is really the first mechanical resonance, even when you go far. And so even if you assume that you're not resonant with the gravitational waves for the electromagnetic transition, and also for the mechanical transitions, because those are kind of given to you once you build the cavity, then that's the curve that you get. So this non-scanning is literally attaching MAGO to some springs and let it run for a few years. The other curves that look much better or a little bit worse instead require being resonant with the gravitational wave, which, well, on the one hand, demands a lot of time. And this is true also for these dashed lines you see for other experiments. So these levitated sensors or DM radio, etc., etc. So on all these curves, including our solid lines, you are assuming that you're resonating with the gravitational wave, and that it's taking you 1 year to scan 1 E-fold in frequency. And this, without even counting the time it takes you to recalibrate the experiment at every frequency. So in practice, if you really want to achieve these sensitivities, you need to run your experiment for many, many years, even decades. And of course, ultimately, you get better sensitivity because resonating is always better, but okay, obviously it comes at a cost. If you want a few more details, well, the difference between the solid lines is what we assume for for mechanical vibrations at high frequencies. Unfortunately, we were not able to find any measurement beyond a few tens of kilohertz. So if you're aware of that, I'd be super grateful to you for pointing it out. So what we did was essentially to assume that the force power spectral density was going down like 1 over frequency. Okay, that would require another 5 minutes of commentary. So if you ask me, I'd be happy to say why we chose that. All I'm going to say for those that don't care about this kind of details is that I believe that this is a conservative assumption. Finally, well, there is not much more to say qualitatively about this figure, just that the blue and the purple differ by the fact that the purple is targeting the mechanical signal and the blue is targeting what I call the electromagnetic signal. So here you can see immediately that there is a huge difference between the two. It's really like so many orders of magnitude that it's not even worth to think about the electromagnetic signal. The only reason why one might care about the electromagnetic signal a priori is that you can imagine to have some active feedback system that completely kills vibrations. Okay, in that case, you see zero mechanical signal, because your mechanical signal comes from the fact that the walls of the cavity are moving, but you still see an electromagnetic signal because the gravitational wave is still coupling to the photons in your apparatus. But even if you imagine an idealized feedback system that can set to zero all vibrations, which I don't believe exists, still the mechanical signal with vibrations dominates over the electromagnetic signal without vibrations. Okay, so to conclude, well, okay, if you find this sensitivity interesting for your proposed signal, well, stay tuned, because we hope to put out the paper with this set of authors at the bottom of the page, hopefully before the end of the year. So, well, thanks for your attention. To summarize, I just showed you that you can recast some action dark matter experiments to bounce high frequency gravitational waves. And I discussed a very old concept for gravitational wave detection, which I think could actually teach us something interesting in the future. And as far as concrete progress goes, this is not just a theorist dream. So both Fermilab and DESY are interested in building a prototype for this kind of gravitational wave experiment. I think that at the moment they are fighting over who gets the MAGO cavity to start doing preliminary measurements, but eventually I think one of them will get the cavity, and hopefully the other one will build their own prototype. We will see. On the DESY side, okay, the money are not so set yet, but I think at Fermilab they have so many cavities that they use for other stuff that they could just use one for gravitational waves, and it would be not, okay, completely optimal like the projections I've shown you, but still order one close to it. So, okay, thanks for your attention, and I'm happy to take any question.
Thanks a lot, Raffaele. This was very interesting. So we are 6 minutes over time. So unless there is some very urgent questions, I will postpone maybe the discussion to later.
Yeah, I should say that unfortunately I'll be on a train during the discussion session, but okay, if I don't want to delay you, so if you can still, I mean, whoever wants to ask, they can email me or.
Okay. I don't see urgent questions, so thanks again, Raffaele.
Thank you very much.
And we can go to the next speaker, who is Tessa
Hi.
Baker. Hi.
Let me share this, and if I do that, that works, and you can see my mouse, I think.
Yeah.
So
yeah,
you're all good.
Yeah, so Tessa from Queen Mary University of London will tell us about testing gravity with gravitational waves. You can go ahead, Tessa, you have 30 minutes.
Okay, good. Yeah, I actually prepared slightly less than 30 minutes to allow some time for questions, so we should be fine. So hi, everyone. It's very nice to speak to you all this afternoon. So as you can see on the slide, I want to tell you something about how gravitational waves can be used to test the laws of gravity that are operating on the largest distance scales in the universe. And that kind of quest, of course, is motivated by our efforts to understand cosmic acceleration, right? Which so far we do not seem to have kind of good, satisfying theoretical explanations for. So that's the arena we're working in. There we go. So there are 3 things that I hope to cover today. I'll start off by indicating something about how we expect the propagation of gravitational waves to look different if we have a theory of gravity other than general relativity. And then I'll focus in the next 2 sections on 2 particular parts of that phenomenology. So we'll start off by talking about the speed of gravitational wave propagation, and then we'll talk about something called gravitational wave friction. The speed of propagation is something that was sort of talked about a lot a few years ago. Maybe I'll just advertise that there's sort of a standard result that was well publicized, but there's been a few things that have happened since, which might be new to some of you. So just before we get going, let me stress that today's talk is all about gravitational wave propagation and not about gravitational wave generation. So I am not going to consider modifications of GR happening in a strong field regime, actually inside a binary. Those are considered, but that's a whole other branch of work and a whole other talk. Today, we will be assuming that galaxies are protected by a screening mechanism. So something which reduces your extended theory of gravity to GR in certain environments, usually high density environments, so that your source and your observer both live in galaxies that are governed by GR. And what we're really focusing on today is the set of things that can happen as your gravitational wave travels across intergalactic distances and feels the kind of fully unscreened effects of your new gravity theory. Okay, so that's the setup. Let's talk a little bit more about how this propagation phase looks in theories of gravity outside of general relativity. So to start with, we have an equation that describes a gravitational wave propagating on an FRW background, so a smooth expanding universe in general relativity. Now, of course, the real universe is not FRW, it has structure in it, but that's a kind of a small correction to what I'm saying today. So this is a wave equation for this object Hij, which is your spin-2 perturbation of your metric tensor. So this is your gravitational wave. And you can see it's a wave equation. It's got a second order time derivative. It has a second order spatial derivative, but we've gone to Fourier space already. So that's become a factor of k squared. And hidden in this object are your two polarization modes, which we call the plus and the cross. Now, not only is it a wave equation, it's a damped wave equation because it has a friction term, which sits here. And you can see that the friction term depends on the Hubble factor. So it's somehow sensitive to the fact that the gravitational wave is traveling through an expanding universe. Okay, that's the situation in general relativity. Let's see what can happen to this equation as we go to an extended theory of gravity. There we are. Okay, so the equation's got longer. There's 4 new terms that have appeared. I've colored them in to sort of help you see them by eye. And I want to stress that these terms I'm showing, or this equation, sorry, it is not representing any particular theory of modified gravity. You should think of this as a kind of template for all the different things that can happen in several different theories of gravity. Okay, I've just put them all into one. So what's happened? First of all, we've got a new term appearing in this friction term of the equation. I've parameterized that by some parameter I'll call alpha m. And your intuition should tell you if you're going to change the friction term, that's somehow going to be related to changes in the gravitational wave amplitude. Then there is the speed of propagation, which of course in GR is equal to the speed of light, which will be 1 most of the time today. But if you have a different speed, so CT, T for tensor mode, that will appear here. We can have a mass term for our gravitational wave, or for our graviton rather. So in GR, of course, the graviton is massless, but we can allow that to appear. And we can also have a non-zero source term on the right-hand side of this equation. Okay, so again, in GR, this is 0 once your gravitational wave has kind of cleared its source environment. But now we're allowing it to be non-zero. Maybe there's something that couples to or sources your gravitational wave as it travels. And finally, I couldn't really show it on the equation, but we also have the possibility when we go beyond GR to excite extra polarization modes. So to go beyond the usual plus and cross modes of GR. And so these things on the slide here provide a set of phenomenology that we can go look for, or at least try to constrain with data. and thereby constrain the presence of any deviations from GR. Now, these set of sort of things here are in varying states of constraint and usefulness right now. So, for example, the best constrained parameter here to date is the mass of the graviton, which is well measured in solar system experiments, or well bounded, I should say. Conversely, probably the least measured part of this right now are the presence of extra polarization modes. And that's just to do with how the current terrestrial gravitational wave detectors are set up. They're not particularly well aligned for polarization measurements. That will get better when the CAGRA detector has more observing time and we continue to build more ground-based detectors. Not all of these effects are equally interesting. So, for example, this non-zero source term is quite rare. And by that, I mean, there aren't many theories of modified gravity that actually turn that part on. Whereas conversely, this modified friction term is really generic. It happens in lots and lots of gravity theories. So I can't talk about everything here today, but what I want to do is tell you about perhaps two of the most relevant parts of this in more detail. So I'll first talk about this modified propagation speed, and then if time permits, we'll come and say a little bit about this generic modified friction term. Okay, so we'll start with the propagation speed. And I've got some nice pieces of art here, which come from a UK artist called Penelope Cowley, and she likes to do these kind of science-inspired pieces. So this one is Cosmoparticle. Okay, so the propagation speed. Let's start with the standard story that has been quite well publicized, I think. So this story starts back in 2017 with the detection of the first standard siren, the first binary neutron star merger, GW 170817. And because this was a multi-messenger event, that means we got gravitational waves as well as an electromagnetic counterpart. The timing of the arrival of both of those signals allowed us to put a constraint on their relative speeds. So in the middle panel here, you've got what we call a spectrogram. You can see the frequency of the gravitational wave signal chirp upwards towards merger. And then less than 2 seconds later, you have in these flux counts from 2 gamma ray spectrographs, you can see the start of the gamma ray counterpart here. Okay. And so the fact that these 2 signals arrive 1.7 seconds apart, quite a simple calculation, it's done in the papers in the top right there, converts into a bound on any difference in their speeds. And that bound is usually quoted as a fraction, so the difference of CT relative to C. And that bound is quoted in rough terms as being less than 10 to the minus 15. Okay, so an incredibly small number, and therefore, as far as we can tell from this one data point, gravitational waves travel at or very, very, very close to the speed of light. Now, this is only one data point, and it's a data point at quite low redshifts. You can argue with that, but for today, let's assume there's nothing special about low redshifts, so that we don't suspect anything different to happen at higher redshifts. And the claim back in 2017, made by several groups, including myself, was that this ruled out a lot of what we call Horndeski gravity theories. And this word Horndeski just refers to a big family of modified gravity and dark energy models, which basically subsumes things that look like GR, so they have a metric, plus 1 extra scalar degree of freedom. So all the big names like quintessence, k-essence, Galileons, they're all members of this Horndeski class. Okay, and the claim was a lot of them were ruled out. So that was the story a few years ago. However, about a year later, it was pointed out there's a little bit more of a subtlety here, which was kind of not understood at the time. So in particular, these analyses assumed that the speed of propagation of gravitational waves was a constant. So it doesn't depend on frequency. And actually, it was pointed out by Diram and Melville from Imperial College London that that might not be the case. And this is the statement they made. What they did was they took that Horndeski family of scalar tensor gravity models and they treat it as an effective field theory. Okay, so they treat it as a low energy description of some higher UV complete theory of gravity that we don't know about. Okay, when you do that, of course, that implies that, like any effective field theory, there has to be a cutoff, a scale above which you do not trust your theory. And when they went and computed what could that cutoff scale be for this Horndeski family, using some kind of, reasonability arguments, let's say. And they found that this cutoff scale could be as low as a few hundred hertz. Now that's interesting because that's actually towards the lower end of the band probed by terrestrial gravitational wave detectors. And what they showed, and this is a figure taken from their paper, is that it's possible to have Horndeski models which would have a speed of propagation, CT, that is different from 1 at low frequencies. Okay, and that's what you're seeing in this kind of rainbow region where the color is just some parameter in their model that we don't have to worry about today. But that these models can undergo a transition back to 1, the speed of light, at high frequencies. Okay, and that high frequency limit is required by demanding Lorentz invariance at high energies. And what you can see from the gray bands on this figure is, of course, that the ground-based detectors probe mainly that high frequency regime where everything has gone back to C. And it doesn't automatically rule out the existence of deviations at lower frequencies. So this question of the propagation speed is kind of back open again. We know we've probed it in a certain regime, but we haven't kind of settled it in lower frequency gravitational wave regimes. And you can see here that, of course, the LISA satellite, which probes or will probe millihertz frequency gravitational waves, and possibly pulsar timing arrays, PTA, which probe even lower frequencies, those experiments might be in a good place to actually kind of recheck this bound. And that's something that should be done with these new experiments. So if this kind of phenomenology was happening, how would we know? What would be the thing to go look for? And this is something that I and my collaborators have studied in a lot of detail. I will kind of give you the very, very condensed version today. And the condensed version is that your best way to probe this kind of transition in speed would be from a multi-band gravitational wave event. So a multi-band event refers to one which is detectable in both the LISA and the LIGO bands. Okay, that's what you're seeing in this plot where the purple is the LISA sensitivity curve, orange is a LIGO curve. And these blue tracks correspond to these multi-band sources, which start off in the LISA band, maybe up to 10 years before merger. And then as they evolve, they in-spiral, they move right towards higher frequencies, and they undergo the merger. That's the sort of knee here. Oops, sorry. They undergo the merger, and then they merge in the LIGO band. And the sort of typical source would be a fairly heavy stellar mass black hole binary. So something like 150914 would have been a multi-band event if we'd had LISA flying, 10 years ago, for example. So, okay, that's a multi-band source, but what happens if it goes through this kind of transition in gravitational wave propagation speed? And it turns out that the sort of most dominant part of the effect would be a shift in the coalescence time of the binary. So you'd observe your binary in the LISA band, you'd see many cycles, you'd measure its parameters well, and using your assumed theory of GR, you would make a prediction for when that binary should merge. And that's a well understood calculation. So we write the timed coalescence as T minus TC, and we can set that equal to some GR contribution. But what happens if you have this change in propagation speed somewhere between these two bands is that you get a correction. And this correction has two factors. So there's a factor d over c, where d is the co-moving distance. So this is a time of propagation of the gravitational wave. It's a large number of order billions of years. And then it's multiplied by this fractional change in the gravitational wave speed itself. So we can set that to something tiny, something consistent with the LIGO band, like 10 to the minus 15. And if we have something large multiplied by something very small, depending on the numbers, we may or may not get something sort of moderately sized. And actually what you find for an event like 150914 is that you would get a shift in the coalescence time of the binary of about 2 minutes. Okay, now 2 minutes might not sound like much, but that is actually very easily detectable by this experimental setup. So with the LISA data, you would expect to forecast your coalescence time to an accuracy of maybe 10 or 20 seconds. Of course, the ground-based detectors will measure that coalescence time to an accuracy of milliseconds. So 2 minutes is not a problem. And of course, if you don't see that shift in the coalescence time from where you expected it to be, that in turn gives you a bound on any possible change in that propagation speed. Okay, and it turns out the bound is back at the level of 10 to the minus 15 or even 10 to the minus 16. Okay, so a single multi-band source would be enough to reinstate that level of constraint that we thought we'd obtained from 1708-17, and then we realized actually required a bit more checking. Okay, but one of these events will allow you to reestablish that at least down to LISA frequencies. So that's probably the best way to get a handle on this modified propagation speed. If we're unlucky and we don't have multi-band events, there are other ways to do it, and they are kind of being hinted at by this subleading corrections here. So there are other changes to the waveform, which if you have something that is only visible in the LISA band, so something like a massive black hole binary, you can go look for. And what I'm showing you in the figure here are some tracks for LISA binaries, so supermassive binaries, where in green you can see the GR prediction, and in red you can see there's these kind of distortions to their tracks, and these are from events, again, going through a modified propagation speed. Okay, but with LISA alone, the effects are much more subtle and much harder to detect. So you're probably looking at constraints of about 10 to the minus 4 compared to the constraints of 10 to the minus 15 that we had on the previous slide. So things are much harder. Okay, that was all I was going to say about the propagation speed. In my last kind of maybe 5 minutes or so, I want to talk just a little bit about another aspect of that modified propagation that we said could be quite generic and quite detectable, which goes by the name of gravitational wave friction. So we're back to this equation here that I showed you earlier, and recall I said you can have a change to this friction term here, and that instinctively should kind of friction in your mind should be linked to a damping of the gravitational wave and to a change in the amplitude. Okay, so let's look at this a little bit more. So your gravitational wave amplitude, to first order, so kind of leading order approximation for a very simple system. So let's take a pair of non-spinning black hole binary on a circular orbit, all the simplifications. The amplitude of your gravitational wave is given by an expression like this. So it contains the redshifted chirp mass, that's curly m. There's a bunch of angular factors to do with polarization and inclination. But also, and importantly for today, there is a distance sitting on the denominator here, which is the luminosity distance. And that's just one of these many standard distance measures that cosmologists like to define. However, you can show that if you go and change the friction term in the gravitational wave equation, I won't take you through the calculation today, but it's easy to show. What that will do is it will change the effective distance that sits in the denominator here. So this new effective distance we inventively call the gravitational wave luminosity distance. And the key point is that it is no longer equal to your standard luminosity distance that you would use in electromagnetic measurements. And so people have sort of now started considering this distance ratio as a kind of smoking gun for tests of gravity and dark energy. And of course, in GR, this distance ratio would just be 1. These would be the same thing. So any deviation of this ratio from 1 might be an indication of new physics. Now, you can go work out a prediction for this ratio in a particular gravity model, but what's become quite popular is instead to work with model-independent parameterizations of this ratio. So you come up with some functional form which you think describes this ratio in a motivated way. And I'm showing on the slide here one such parameterization that's again been quite widely used. It's controlled by this parameter in green, which is xi0. And basically, if xi0 is 1, the whole expression reduces to 1 and you're back to GR. And if xi0 is greater or less than 1, you have some evolution of this ratio. Okay. And the precise shape of these curves and the sort of functional form here are motivated by looking at some mainstream modified gravity theories in a way we sort of won't go into today. So then the question is really to try and constrain this parameter xi0. Now, there's various methods for doing that. You could try and do that with a standard siren like 170817. However, we've only got one of those so far, and 170817 is actually at very low redshifts. So it's not very good for this measurement. You can see these curves deviate at high redshifts, and so you really want something further away. So the current sort of front-running way to constrain this xi0 parameter is instead using a technique called dark sirens. So what happens in a dark siren method is that you don't have an EM counterpart, but instead you try and use all the galaxies that you see in the localization volume of your gravitational wave event to pin down the redshift of your gravitational wave event statistically. And if you can get a redshift, you can convert that into a distance. Okay, so what you're seeing here on the top left is the kind of localization of the gravitational wave on the sky. In the middle is the kind of 3D projection of that, so the volume of space the event's been localized to. And of course, you can go look at those parts of the sky with a telescope. So there's a whole beautiful statistical Bayesian formalism that underpins this measurement. I definitely do not have time to go into that today, but I do have some references on the next slide. But this is the way we think that xi0 should be measured. So just instead to sort of show you some real world results from this method. So on the left-hand side is one of the plots from one of the LIGO papers where they do this dark sirens constraint. And what you're seeing in green is the gravitational wave data for a particular event. In red is the galaxy catalog, the distribution of galaxies. And this dark siren statistical method has a way of basically evaluating how much support there is of these two overlapping distributions. Okay, and I realize I'm skipping the details, but what you will get out of that is a bound on xi0, okay, which remember was the parameter in this distance ratio. And so in gray here, you see the contributions from all the different events in the LIGO 03 dataset. And in red is their combination. So at first glance, this looks really nice. You've got a nice sort of, well-constrained measurement of xi0. It's peaked close to 1, which is the GR value. So everything looks really good. However, I'm going to say loud and clearly that you should not trust this plot. And that's because there's a problem with this measurement, which we're really working hard on right now for the next LIGO observing run, which is in this particular analysis I'm showing you, we only constrained this xi0 parameter, and we did not allow the parameters describing the mass distribution of gravitational wave events to vary. And it turns out that's really important. So if you basically your modified gravity parameter is going to be degenerate with some of those mass hyperparameters. So you cannot just constrain this thing by itself. Okay, and that's why this constraint is over optimistic for now, but hopefully when we have more data and we are doing the kind of full analysis, this will be better. I'm going to skip that slide, I think, in the interests of time. So this is just kind of stressing the point that I said, that really this dark sirens analysis you want to do for cosmology has to go hand in hand with the astrophysics. And there's existing codes to do each of these measurements. It's GW Cosmo for dark sirens. There's a code called ICARO GW for the mass distribution. And the kind of bleeding edge of dark sirens research right now is putting these two quite substantial, quite meaty analyses together. But we hope that that's a problem that we should be able to kind of update on when we have more gravitational wave data available. Okay, I'm going to wrap it up there for today. So just to kind of reiterate visually what I've told you, we looked at the propagation equation for gravitational waves in modified gravity. I told you a story about how the speed measurements are not as straightforward as they seem, but a single multi-band event is probably the best way to get a handle on those. I also talked about this gravitational wave friction measurement, but I explained that can't be separated from the mass distribution. And I didn't dwell on this plot, but this is basically a plot of that mass distribution. So cosmology and astrophysics have to go together when you use gravitational waves to do tests of gravity. Okay, I'll leave it there, and thank you very much for your attention.
Yeah, thank you, Tessa. This was very, very interesting. I didn't know so the bounce that we had from 2017 are not there anymore. This is very interesting.
They're not there, but there's
okay, we get
caveats,
yeah, as you explained. So any question? I don't see any question now, so probably the best thing to do is to just postpone the discussion to the next session. We should reconvene at 4:30, so in 23 minutes. And let me remind you that the speakers are requested to participate in the panel discussion, which will close the day. So thanks a lot for being here, and see you soon.